My name is Amitabh Basu, and before I begin, I have two quick caveats to make. Firstly, I'm a bit of an outsider to this community, by which I mean the machine learning and statistical learning community. I really come from optimization, and within optimization, discrete and combinatorial optimization. However, it's an I'm especially grateful to David and the organizers here at SAMSI for giving me this opportunity to speak. I have been thinking about problems in learning for the last maybe a year or two, and I think there are, like Xiaomin said, many interesting problems to think about. This talk actually is going to be more about maybe statistical aspects about learning rather than the optimization, even though I come from an optimization background. And that brings me to my second caveat. The talk is going to be about a slightly broader problem, not particularly about deep learning, but about the more general stochastic optimization problems underlying deep learning and machine learning in general. Okay. So with that, I'd like to introduce my co-authors, which are two PhD students at Johns Hopkins University, where I'm from, Tu Nguyen and Ausen. Okay, so let me dive straight into the problem that I want to discuss. It's a very general stochastic optimization problem, which is studied in many different communities, including operations research, optimization, computer science, and certainly learning and statistics. Okay, so just to introduce everybody to the model, I'm going to consider this function of sort of two arguments. The first argument is going to be sort of a decision variable that we are trying to solve for. And the second argument is a random variable, which introduces the stochasticity in the problem. Okay. And the main optimization problem that we would like to understand or solve is this problem, where we take an expectation over the second argument, and we want to find the value of the first argument that minimizes this objective. Okay? If you crack open any book on stochastic optimization, this will be the first thing that you see in chapter 1. Okay, so for me, this was a little bit of a new thing to wrap my head around, because I come from a deterministic optimization background. So just to set the stage, I'm going to give you two examples that this model can actually be useful for, one from learning and one from operations research, and then we'll dive into what I'm really interested in talking about. Okay, so the first example, which is most relevant to this workshop on deep learning, is supervised learning. So in my mind, machine learning, if you just extract out the abstract mathematical problem, it's the problem of approximating a distribution using a function from some hypothesis class. Okay, so in particular, what you see are samples, label samples in the case of supervised machine learning, of some features. Here I label them with Z, and a label Y of these features, and they are drawn from some distribution, and you want to approximate this distribution using a function from a hypothesis class F, which could be the class of neural networks of a particular architecture. Okay, and what's the goal? Well, the goal is that this function that you select should have sort of low error with respect to this distribution, which is formalized using a loss function, right? So the loss function operates on pairs of labels. If you give it two labels, it tells you how far these labels are. And what you want to do is minimize this expected loss. So you have your function on every feature. It gives you some label, and the loss function will tell you how far this label is from the expected label for that feature. And that's the thing you want to minimize, right? And this easily falls into that framework if you just do a simple pattern matching. In particular, the space X over which you're searching is your hypothesis class. Okay, so you're searching over all functions from this class of functions, and your random variable is this sample from this distribution that you're trying to approximate. Okay, and if you set this function capital F from that model to be this loss applied to F and this and the sample, then that's exactly that problem that you're trying to solve. Okay, very simple. Okay, the second example, which is like a canonical thing again that you'll see in chapter 1 on any stochastic optimization book, is sort of an operations research problem, which is known as the news vendor problem, where it goes as follows. So you have some kind of a vendor who can buy some units of a product, let's say newspapers, from a supplier, and then he's going to go to the market and sell those. Okay, so he can the cost of buying this product from the supplier is some C dollars per unit, and let's say there is some budget constraint or some supply constraint that you can buy at most U units. So you can buy anything from 0 to U units. And when you go to the market, you ask for some price P, which is bigger than the cost that you paid per unit. But the problem is that you don't know in advance what the demand is going to be for this product. Okay, so it's going to be a stochastic demand. And at the end of the day, if let's say you have some leftover units at the end of the day, you can sell it back to the supplier, of course, at a sort of discounted price R, which is less than the cost that you bought it at. Okay, and your goal is to maximize your expected loss, where the expectation is over the stochastic demand. Okay, so again, this can be easily formulated as that general stochastic optimization problem above by just saying the following. Okay, so X is exactly what you have to decide, how many units to buy from 0 to U. Okay, and if you want to make it a discrete problem, you can say that, okay, you cannot buy half a newspaper, you have to buy either 1 newspaper or 2 newspapers. Then this would be a discrete optimization problem. You can either have 0, 1, 2, or U, or it could be a product that you can have a continuous range of values. So X can be continuous or discrete, doesn't matter. But the objective, without the stochasticity for a second, is that if you buy X units and the demand was this psi, which is a random variable, then of course you pay Cx at the beginning to the supplier, and then you recover P times the minimum of X and psi. So if you have less demand, then of course you only get P times psi, but if you have more demand than what you had, then you can only sell what you had, right? And then at the end of the day, you sell back whatever was left over. Okay, so this given a particular X that you bought and a psi demand that was realized, this is what your profit, actually loss would be, right? And now you really want to minimize the expectation over the stochastic demand side. Again, so it's exactly that problem. So many, many different stochastic problems can be put into that framework up top. Okay. Any questions about that framework? Okay, good. So what does it mean to solve the problem? So if you look at sort of the operations research literature, or the stochastic optimization literature, a majority of the methods would do the following. They would assume some information about the distribution of this random variable. They might assume the exact form of the distribution, or they might assume the expectation or some moments of that distribution. And then what they'll do is proceed to write this expectation as a closed form formula using what you know about this distribution. Okay, so maybe you can evaluate this integral in terms of the expectation and the higher order moments, and then you get some expression, and it becomes a deterministic optimization problem, right? Because the expectations have been replaced by parameters of the distribution you assumed. And then you use all of your technology from optimization theory and algorithms to solve that problem. Okay, but the learning or the statistical approach is slightly different. So here, what it means to solve the problem is that you don't assume too much about the distribution of psi. As opposed to that, you assume that you get some samples from that distribution. That sample gives you some information about the distribution, and based on that, you make some decision about what little x to report. Okay, so there's a sort of a paradigm change in moving from the operations research point of view to the sort of statistical point of view of solving this problem. Okay, and I'm going to focus on exactly this way of thinking about things, because this is a workshop on learning and not really operations research. Okay, so a natural idea, which of course in practice stochastic optimizers would also advocate is to use those samples and replace that expectation with an empirical average. Okay, it seems a very natural idea. Now your problem is a deterministic problem. Okay, there is no stochasticity anymore here. You solve this problem in X, and that's your solution. Okay, seems like a very reasonable approach. Okay, and in the literature, in the OR literature, you would see this as the sample average approximation method. And if you look at the learning or the statistical theory community, you would see this as the empirical risk minimization problem. Think back to that deep learning example that I put in that framework, and this would exactly be the empirical risk minimization problem. Okay? So at this point, I want to point out 3 things about this kind of an approach to solving stochastic optimization problems. The first one is that because you are setting up this deterministic optimization problem based on a sample, the solution you give depends on the sample. So actually, that sample, the solution you give is a random variable. If you see a different sample, you would solve a different problem, and your solution would be different. Okay? So somehow you have to, one has to, when we are comparing how good a particular solution is, we have to take into account that randomness in the solution itself. Okay, the solution is a random variable. The second point I want to make is that this is just one way of using your data. Okay? For example, in the context of deep learning, what you could do is you could set this up, add a regularization term, and say that is going to be my new solution, not this. Okay? Or you could say that, okay, set up this problem, but don't solve it to global optimality. Take a local solution, and that's your solution. Okay, so there are many ways you can use your data, not just in this particular way. And the final point I want to make is that no matter what you do to solve this problem, you want to have a method that works well for a lot of different distributions on that random variable. It shouldn't be that there's only one particular kind of thing that this works well for. You should be robust against many different distributions, okay? So we're going to keep these 3 points in mind as we sort of go through this talk. So let me actually make the problem very concrete. I'm going to look at this particular bilinear problem, which is the inner product of psi and x, which means now I'm assuming that x and psi are living in the same dimensional space, which in the original problem, you don't have to really assume that. Capital X could be in a different dimension than M. Okay. I'm going to also assume that my decision space, the set capital X, is some compact set, okay, in RD. So you could, for example, if you're thinking of linear programming, you would assume that you have a polytope. Or if you're thinking of integer programming, which is what I like to think about, you would be thinking about integer points in a polytope. Or it could be some other compact set. I'm not assuming any real structure other than compactness. Okay? And the further assumption I'm going to make is that the random variable psi is actually normally distributed. But what I don't know is the mean or the covariance of this normal distribution. Okay? So think about maybe a linear programming problem where you're trying to optimize a linear objective over a polytope or a polyhedron. And there is some true objective, but what you get to see are some noisy versions of that true objective where the noise comes from this Gaussian noise. Okay, so think about that. And now you want to solve that linear programming problem or integer programming problem. Okay? Okay, so if you now look at this stochastic optimization problem, its form is actually quite simple. Its expectation, because it's a bilinear term, just becomes this value. So essentially, if let's say capital X was this polytope, you have an honest-to-God linear program. The only problem is you do not know what mu is. You only get information about mu by these samples coming from that distribution centered at mu. Okay? Okay, so that's what I want to say. Okay, and then again, one could set up this sample average approximation proxy for it, right? So I don't know what mu is, but I have some samples. Well, let's put this empirical average, which means that I look at the, because it's bilinear again, you look at the average of your samples, that's bar psi, and you optimize over your set capital X in that direction. It gives you some solution, and that's what you report as the solution, okay? So again, let's think about the three things that we talked about before. First, what I report here is going to be a random outcome, right? If I get a different sample, the average of those samples is going to be different, so I'm going to optimize in a different direction, so I'm going to report a different value. Okay, so I'm going to have to think about what I mean by this being a very good method, because when the outcome itself is actually random. Okay? The second point is that you could have used your data in many different ways. This way just takes an average and optimizes in the direction. Here's another crazy way. If the first coordinate of the first sample is greater than 10, then take the inner product of the second and the third samples and scale the fourth sample by that and optimize in that direction. It could be some other rule that you come up with. It's not intuitively or immediately clear why this method is better than this other crazy rule that I came up with. Okay, so I want to make create a theory that kind of compares rules and says, okay, this is a better rule than what you came up with. Okay, and then the third point was that no matter what I do with my data, the final solution I come up with, it should be a good solution no matter what mu is. I don't know what mu is, but I could have, this problem could have been set up for any different value of mu. And what I report finally should be good for all these different values of mu. So I have to take into account all of these three different issues. And in my mind, statistical decision theory actually has a very, very nice framework for thinking about these three issues that I brought up. Okay, and I'm sure most of this audience is actually much better equipped with the concepts of statistical decision theory than I am, and I really learned about all this stuff in the past year, and I find it very, very fascinating, and the ideas are extremely interesting and applicable. Okay, so just to sort of recap what ideas of statistical decision theory I'm going to use. So the basic problem of statistical decision theory is the following. You have some states of nature which are not known to you, okay? But you believe that you live in some state, one of these states of nature. And you have a possible set of actions to take, okay? And now depending on what state of nature you are in and what action you take, you have some way of evaluating how good that action is for that state of nature, okay, by something called the loss function, okay? And the goal is, of course, to basically minimize this loss by choosing an appropriate action. Now, the point is that we assume that we have complete knowledge of the loss function, but what we do not know is what state of nature we are in. Because if we did, then we would exactly choose the action that minimizes this loss. But we get some information about the state of nature by observing a random variable, y, whose distribution depends on the state of nature, okay? So you see some samples of this random variable, and then you make a guess from that sample that, okay, this must be the state of nature I'm in, so let us take this action, okay? This is the setup, and a decision rule is basically a function that maps a sample to an action. Because all you see is a sample, you don't see the state of nature, so you have to tell me what you're going to do when you see a particular sample. Okay, so this is a decision rule. Okay, so let's try to cast our problem in this framework, right? So remember what we had. We had this compact set, and we are trying to optimize in this direction mu, but I only get to see samples from a Gaussian centered at mu. Okay, and so that's what I'm trying to do. So the states of nature, in this case, are all the possible mu's. I don't know what mu I'm getting. Okay, if I knew which mu I was solving for, I would know exactly which action to take, right? In particular, the action would be all the set of points in capital X. Okay, I would take the action that would minimize this inner product. But I don't know which mu I am in. But I need to be able to evaluate that, okay, if I was in a particular state of nature mu, and I take some action X from capital X, how good is that solution? Okay? So in the context of optimization, to me, the most natural loss function would be this. Let's say I'm in a state of nature mu bar, and I take some action X bar from capital X. Well, that X bar has some value of the objective, which is the expected objective I'm trying to solve for. And this expectation is over psi parameterized by that mu bar, right? That's the value I get for my action. And I see how much better the best action possible was for mu bar. Okay, so now I minimize over all x in x of that objective. So I'm seeing how bad my decision x bar was compared to the best decision possible in this state of nature. That's my loss function. Very simple. Okay? So if you evaluate that for that exact thing, it will just be this, right? So remember that expectation is just mu transpose x, so that will be just exactly this, where x mu bar is the best point in your polytope or your set x with respect to this objective mu bar. Okay. What is the sample space? Well, the sample space is I get n IID observations from the Gaussian centered at mu bar, right? Okay. So a decision rule is going to look at all of these data points, and I'm going to report some point in capital X. It's very simple. Okay, and the sample average rule does the following. It takes an average of all the data points and optimizes in that direction. Okay? So let's visualize that. Let's say that we have a two-dimensional problem. The set capital X is this square, so you have to report some point from this square, right? And you have some mu pointing in some direction, and you get some observations from the Gaussian around mu. And the sample average approximation would do the following. Take an average of those data points, and if, let's say, that average falls into the first quadrant, which is labeled 2, then you would report that corner 2, because that's the best solution in your square with respect to any vector in that quadrant. Similarly, if your empirical average fell into this quadrant labeled 1, then you'd report that corner labeled 1. Okay? That's the sample average rule. But like I said, you could come up with any other rule using your data. For example, you could still look at the empirical average. You could say, okay, if it falls into that pink area, then I'm going to report 1. If it falls into that yellow area, I'm going to report 3, and so forth. You don't have to go for that quadrant-based rule at all. Okay? And how do you decide whether this is better or that quadrant rule is better? In fact, you could have some very crazy rules. Look, like Daffy Duck here. So if your average falls into the black areas, you're going to report the center of the square. If it falls into its head, you're going to report the rightmost corner. Any crazy rule like this. Okay? And you have to really decide why is that quadrant rule any better than Daffy Duck? Okay? Okay, so how does one decide? Good, so let's go back to this more general framework of statistical decision theory. You have states of natures, you have actions, you have a loss function, and you have a sample space that gives you some information about the state of nature. Okay, and you have a decision rule, and you're trying to decide how to, you're trying to figure out how to decide between two decision rules. So define the risk function of a decision rule, which takes care of the stochasticity of the decision rule, right? So remember, there was the first point I raised, that depending on the data, I would report different things. That's exactly what the decision rule is doing, right? Depending on the data, it reports different actions. So given a state of nature, I'm going to average over all the different samples I could have possibly obtained, okay? So that's what is called the risk of this decision rule at this state of nature. Okay? And now I'm going to really look at this as a function of states of nature, because I really want to be doing well with respect to all states of natures. Okay? So every decision rule is going to give me this risk profile, which is a function from the set of states of nature to a real number. Okay, so I've taken care of the stochasticity by just taking a very simple average over the data that I see. And I'm taking care of the fact that I want to be doing well with respect to all the states of nature by looking at this entire risk profile. Okay? Good. And now we say something very, very minimal in a sense. So I say that a decision rule delta prime dominates delta if the risk for delta prime is uniformly lesser than the risk for delta for all states of nature. Okay? If something like that happens, and there is a particular state of nature theta star where it is strictly better, where delta prime is strictly better, then you certainly want to go with delta prime and not delta, because it's always doing better, and there are some states of natures where it does better, strictly better. Okay? So that's the notion of domination. So that's how you compare decision rules with each other. And you say that, okay, if a decision rule is not dominated by anything else, then it is admissible. Okay? I have not invented these concepts, right? These have been around in statistics since the 20s and the 30s. Okay? And if a decision rule is dominated by something else, it is said to be inadmissible. Okay? Any questions? Okay, good. So the question that I want to basically ask is whether the sample average approximation rule is admissible or not. Very simple. Okay? So again, let's go back to the very general stochastic optimization setup. I want to solve that problem with access to these samples. And the view I took is that psi is distributed according to some normal distribution, and I don't know the mean of the normal. And that's my set of states of nature. I have to take an action from this set capital X. I see some observations. The loss function is how good my action is with respect to the best action for that particular state of nature. And given a decision rule, meaning I see some samples and I report something in X, this is the risk profile for that rule, right? And it turns out that if you do the sample average approximation, this is a rule, right? You get some data points and you report something from X. It's a decision rule. It can be inadmissible. Okay, so this very simple-minded rule can be inadmissible, and this was observed by Stein in the late 50s. It's known as Stein's paradox in the statistics literature. Okay, and the function is very simple. It's actually just the quadratic given by x minus psi, the norm squared. Okay, if you take that objective and you have exactly this setup, then if you just rewrite all these things, then you'll notice that the optimal solution is precisely this mu, okay? Because under this loss, you are actually going to just get the squared loss function. And if you do the sample average approximation, you're going to set this problem up, which means the solution to this is the empirical average, because you're trying to minimize the square distance from all the data points. And Stein proved that this is actually inadmissible. Okay, so if you report this, this is going to be inadmissible. There's another decision rule, which is kind of a very non-intuitive rule if you, for the first time you look at it, which dominates this sample average rule. Yeah, and this was generalized recently to some more general functions, quadratic functions, in this paper from 2018. Okay, so I'm kind of running out of time. So let me just jump straight to the theorem that I want to show. I actually show that if you consider this problem of optimizing an uncertain linear objective over a compact set, then the sample average approximation is actually admissible. There is no Stein's paradox or Stein's phenomena for this particular problem. Okay? Let me sort of go, recall what this means. If I want to show that the sample average rule is admissible, that means I have to defend against all other possible decision rules, including Daffy Duck, right? So I have to show that for Daffy Duck, there is some state of nature where actually the sample average rule does better. Okay? And so let me quickly go through the main technical ideas or tools that go behind proving something like this. So the first idea is that of a sufficient statistic, which of course any statistician is extremely familiar with it. To me, it's the sort of statistician's way of data reduction or data redundancy. And the point is that for the normal distribution, the empirical average is actually a sufficient statistic. And then what you can do is use the celebrated Rao-Blackwell theorem to say that, okay, you don't have to consider all kinds of crazy decision rules. You only need to focus on decision rules that are functions of that sufficient statistic. So in this case, you can just consider decision rules that are functions of this empirical average. Okay? Okay, and then what you do is you set up this function which takes the difference of any decision rule risk value and the sample average risk value. And to prove that the sample average is admissible, you need to show that there is some state of nature where the sample average does better. So then it cannot be dominated by delta. Okay? So what you do is you first observe that f of 0 is 0. This is very, super simple. And then you compute the Hessian of this function at 0. And you show that there is a strictly positive eigenvalue. Okay, if there's a strictly positive eigenvalue and you start at 0, at some point you would be strictly positive and you're done. Okay, so that's basically it. The open questions I have is that I could only prove this for this linear objective, and it would be very interesting to establish this for more complicated objectives like the quadratic objective, which Stein showed that it is inadmissible. But I believe that if you make the set X to be a compact set, it actually becomes admissible. So I can prove this for some special cases of X, but not in its entire generality. And of course, you could consider other piecewise linear objectives like the News-Vendor problem. In the context of deep learning, I think it might be a way to try to understand why reporting local minima is sometimes better than reporting global minima. Maybe the global minimum decision rule is dominated by the local minimum decision rules in this sense of decision theory. Okay, and the meta theorem I have is that from my playing around with this problem, whenever you have a compact set, it seems to actually always turn out to be admissible, at least the compact sets I've played around with. So maybe a meta theorem, which comes from Gerard Cornijols at Carnegie Mellon, is that this stochastic optimization problem becomes, the sample average rule becomes admissible when you have compact decision sets. Okay, that's all I had to say.